Welcome to this explainer. Today, we're taking foundational geometry and, honestly, transforming it into a dynamic, real-world survival toolkit. We're ripping these concepts right off the flat, two-dimensional page to see how they literally map our world. So whether you're navigating an ocean or just, trying to ace your next math exam, the tools we're going to unpack today are absolutely essential. Let's get right into it.
Here's the game plan for today's toolkit. First up, essential bisectors and constructions. Then, loci, paths with purpose. Number 3, bearings, navigating the world. 4, scale drawings, shrinking reality. And we'll wrap up with number 5, exam tips and mistakes. All right, let's kick things off with Section 1, Essential Bisectors and Constructions. This is all about building the foundation.
What's truly fascinating about a perpendicular bisector isn't just the physical cut itself, it's the mathematical consequence of that cut. When you slice a segment perfectly in half at exactly 90 degrees, you're not just chopping a line, you're creating a boundary line of perfect equality. Absolutely every single point along that new line is exactly equidistant from your two starting points, A and B. It's a literal line of balance.
So how do we construct this perfectly without cheating with a ruler's markings? Well, start with your segment AB. Then open your compass to just past the halfway mark. You're going to sweep a nice broad arc above and below point A. Now, here is the critical secret. Freeze that compass width. Do not let it shift. Move over to point B, repeat that exact same sweep, and right where those arcs cross, that's where you draw your line. Boom. Flawless precision every single time.
And hey, we can use that exact same logic to slice a corner or a vertex perfectly in half too. You just draw an initial arc cutting right through both arms of the angle. Then, use those two new intersections to anchor two more equal arcs out in the open space between the arms. Finally, just connect the vertex to that final intersection. Just like that, you've got an angle bisector. And just like before, every single point on this new line is perfectly equidistant from the two original sides.
Once you master these basic movements, you literally unlock a whole arsenal of standard constructions. Think about it. Armed with nothing but a compass, a blank ruler, seriously ignoring the measurements entirely, and a sharp pencil, you can build perfect 60-degree and 90-degree angles. You can construct flawless equilateral triangles or even regular hexagons. It's like magic, but it's math. You don't even need a protractor, because the geometry inherently guarantees the precision as long as your technique is solid.
Moving right along to Section 2, Loci, Paths with Purpose.
Okay, the key shift in thinking here is that a locus, which is the singular form of loci, by the way, isn't just a single isolated spot on a page. Nope, it is an entire continuous path. It's a path traced by a point that is obediently following a strict mathematical condition. It represents all the possible points that satisfy that one specific rule. Basically, it's geometry in motion.
Let's map out some of these abstract conditions to their actual physical shapes. Say the rule is to stay a fixed distance from a single point, well, you get a circle. What if you need to maintain a fixed distance from a straight line? You get parallel lines on either side. And if you need to be equidistant from 2 points, or 2 intersecting lines, guess what? That brings us right back to our perpendicular and angle bisectors. So those constructions we just learned, they're actually just the tools we use to draw specific loci. Pretty cool, right?
All right, let's scale things up in Section 3, Bearings, Navigating the World.
Before we can start moving ships across the map, we really need to define what direction means in a strict mathematical sense. A bearing is simply the direction of one point relative to another point. But obviously saying go over there or head that way is definitely not going to cut it in real navigation. We need absolute, undeniable precision.
To get that precision, navigation relies on 3 absolute, unbreakable laws. Number 1, always measure clockwise. Number 2, always start your measurement from absolute north. And number 3, always write your answer using exactly 3 digits. No exceptions. When we apply these 3 laws, we turn our standard compass directions into precise mathematical codes. North becomes our starting line at 0, 0, 0 degrees. A right angle clockwise to east, that's 0, 9, 0. South is a straight line down, making it 180. West completes the 3/4 turn at 270. And what about northeast? Well, since it perfectly splits the difference between north and east, that gives us 0.45 degrees.
Okay, let's actually test this out with a real-world scenario. Imagine a ship sets sail, heading directly southeast. We know the general direction it's going, but what exact three-digit mathematical bearing must the captain punch into that navigation system to actually get there?
If you guessed exactly 135 degrees, you hit the nail on the head. Let's break down why. East is 090 degrees and south is 180. Southeast perfectly splits the difference between the two. So taking that 90 degrees and adding that exact 45-degree slice brings our captain to a precise, flawless bearing of 135 degrees.
Now for Section 4, Scale Drawings, Shrinking Reality. This simple ratio is honestly the fundamental key to all of architecture, map making, and engineering. A scale dictates exactly how a tiny little length on your drawing translates to massive real-world reality. For example, a scale of 1 to 50,000 simply means that one unit of measurement on your page, say 1 centimeter, represents exactly 50,000 of those exact same units out there in the real world.
So, let's put it to work. If we have a map with a scale of 1 to 25,000, and we take our ruler and measure exactly 8 centimeters between two ports on that map, how far does our ship actually have to travel in the real world?
Well, first we multiply our map distance of 8 centimeters by our scale factor of 25,000. That gives us 200,000 centimeters. But come on, we don't measure ocean voyages in centimeters, so let's divide that by 100 to get 2,000 meters. Then divide by 1,000 to convert it into kilometers. And we find that our 8-centimeter line on paper represents a very real 2-kilometer journey on the water.
And finally, Section 5, Exam Tips and Mistakes. Consider this your survival guide.
When it comes to actually taking exams on this stuff, there are some very strict do's and don'ts. Absolutely do keep your compass perfectly tight. A slipping hinge will literally ruin the math. But the ultimate golden rule? Do not erase your construction arcs. I know it's tempting to clean up the page, but those faint, sweeping pencil lines are your mathematical proof. They show the examiner exactly how you found your answer. Oh, and for bearings, never, ever measure anticlockwise. Just don't do it.
Ultimately, this entire toolkit boils down to a few unshakable relationships. Bisectors manage exact distances, loci bind everything together with dynamic moving paths, and bearings give you the universal language to actually navigate those paths in the real world.
As we wrap up this explainer, I'll leave you with this thought. You now possess the mathematical tools to chart oceans, build perfect hexagons, and find literally every equidistant point between here and the horizon. But in the world of mathematics, simply finding the path isn't enough. Leaving the evidence, those sweeping pencil-drawn construction lines that prove exactly how you found your way, is absolutely everything. So when the time comes, will you remember to leave your mark? Thanks for exploring this toolkit with me today. Keep practicing, and I'll see you next time.